to determine the performance of queuing system. Now, what exactly is queuing theory? Queue theory is the study of how systems with limited resources distribute those resources to elements waiting in line, that is the elements that are on queue, right? And how those elements waiting in line respond to the distributed resources. Excuse me. We can also view queuing theory as a mathematical discipline that studies system intended for servicing a random flow of requests. That is the moment at which the request appears, as well as the time for servicing them. This is usually what a random process. We can also say that queue theory is the study of the behavior of queues and their element. To put it in a simpler form, the study of the behavior of queues and their elements. All right. Now let's look at what queuing system is. I haven't looked at the theory from which queuing system is derived. Now, before we look at queuing system, you realize that queuing system has a lot to do with resources. All right. This is an intersection of operation research. So queuing system has a direct link or origin from operation research. Now, we can say a queuing system is a discrete event model that uses random number to represent the arrival and duration of events. Why do we do that? The objective of a queuing system is to utilize the available servers, such as the teller, the CPU operators, and so on, so as fully as possible, while at the same time keeping the wait time within reasonable limits. All right. The goal usually requires a compromise between the cost and customer satisfaction. You'll see why. If, for instance, there is a supermarket and there's one cash out for every customer, you realize that there will be no queue. Immediately you finish purchasing whatever you want to purchase, you just check out, because there's always what you check out for every customer. But you will be sure that such supermarket will not be in business for long, because they're going to spend a lot of money. It's going to involve a lot of finance to cater for such checkpoints, right? However, there will be customer satisfaction. Now, the number of cashier is kept within limits, all right, set by the store budget, and the average customer is not kept waiting for too long. So there has to be a balance between the number of customers and the time a customer will spend waiting in the system, okay? Now, the question is, how does a company determine the optimal compromise between the number of servers and the customer? That is, how do we strike the balance? How do we know the number of servers that we should have in our company so that we will not run into financial problem, and at the same time not keep our customers waiting for too long before they get served? All right. Now, one way is by experience. When we say by experience, we mean the company tries out different number of servers and see how things work out. This is done by observation. You employ one server, utilize one server, observe the performance, observe the performance of the system. You check the queue and how the customer gets served, the delay in the system. You employ two, employ three, so on and so forth. Okay, now there's a big problem with this approach. There are two major problems with this approach. One of them is that it wastes too much time. It's going to take too much time for the company to determine the number of servers that will be required for optimal performance in that company. And another thing is that it's going to be expensive. It's usually too expensive. It costs a lot of finance to achieve such an experimental approach or experience approach of determination. Now, the other way, apart from the way by experience, is by using computer simulation, where we have variables to represent all of these entities and we adjust this variable, the parameters, to observe the performance of the queuing system. This aspect is the focus of this work, and we'll be looking at that direction in the course of this work. Now, this is a pictorial representation of a typical queuing system. I'm not too good at drawing diagram, but I think this one is simplified enough, and that is simplified enough for you to be able to comprehend the queuing system that we're talking about all this while. Now, this is a typical hospital system where customers will arrive from a population denoted by calling population. We call that a calling population. Now, the customers will arrive at the hospital. In this case, we'll say the customers, they are the patients. All right, they arrive at the hospital and they will wait in queuing area, which is denoted by the queuing area, the queuing where you have chairs, and from there they get served by the doctors. In this case, we have a single doctor here, and when the patient needs being attended to, the patient will what? Depart. Okay, now if there is no queue, the patient will just arrive at the hospital and see the doctor, that is, the patient gets served and depart. But for a typical hospital system, I would say it is actually virtually impossible for a patient to arrive and get served immediately without being on a queue, especially in a country like Nigeria, where you have the ratio of doctor to patient to be very, very far, be very, very large. So we'll say that there's certainly going to be queue when you get there. So the customer comes from a population known as calling population. They get to the hospital, wait on the queuing area, and they get served. And from that point, they depart. This is a simple illustration of a queuing system. Now, having looked at that example of queuing system, we want to categorize queuing system into different kinds. We want to categorize queuing system. There is no one way to look at the totality of categorization of a queuing system. We can categorize queuing system according to the number of server. We can categorize it according to the capacity of the queue. We can categorize it according to the calling population. Now, to begin with, we'll try to categorize it using the number of server. If we have to categorize queuing system according to the number of server, we'll have basically two kinds of queuing system. Don't get confused when you see queue system and queuing model. When we say model, we're referring to the system, okay? We use model to mean system here. Both of them are being used interchangeably. So we could have a single server queuing model or multiple server queuing model. That is single server queuing system or multiple server queuing system. The example of the hospital we illustrated not long ago previously is a typical example of a single server queuing model. Let's take a look at it again. Why is it the single server queuing model? Because the server here, which is the doctor in the hospital, is just one. That is to say, the customer receives service only at one point, which is the doctor. That is what a single server queuing model. Now, for a multiple server queuing model, we have more than one server that is attending to what the entities or the customer or the patient. In the hospital example, we have more than one doctor here. We have Dr. 1, Dr. 2, and Dr. 3. That is the number of server greater than what? 1. This is an example of multiple server queuing models. Now we can also categorize queuing model according to the length of queue. If we have to do that, we also have two kinds of queuing model. One will be the infinite queue length model, and we would also have infinite queue length model. Infinite queue length model, excuse me. Now, for the infinite queue length model, we would have no restriction to the number of entities or patients that join the queue. For instance, let's look at the previous example again. Okay, if you look at this hospital example here, this queuing area or the queue length, let's call it queue length this time, is infinite because there's no time you will get to the hospital, they will ask you to go back because there are too much people. All right. The worst case is that you have to wait for a very long time, but however, you will get served. Okay, this is an example of what infinite queue length queuing model. Infinite queue length model. All right. Now, we also have the finite queue length model. When we say finite queue length model, we are saying that the queuing area or the queue has a capacity that must not be exceeded. An example is a mechanic garage that can take only 10 cars. Okay? The garage can take only 10 cars. If that is including the one that is being serviced. Okay. Now, if there are already 2 spaces left and there's an arrival, the car will still be able to join. All right. But if, however, the spaces are exhausted completely, any arrival cannot join the queue. Such arrival will have to leave because the queue capacity has been what? Exceeded. This is an example of what? Finite queue length model. Finite queue length model. Now, we can also categorize queuing system according to the calling population. If we do that, we will also have 2 broad categories of queuing model. We'll have the infinite population queuing model, or the finite population queuing model. When the queuing model is categorized according to infinite population, we will say that the calling population has is infinite, all right? The calling population is infinite. We cannot determine the size. We cannot determine the capacity of where the entities emanate from. That is what infinite population. An example is the hospital or mechanic garage, all right? Though they have finite and infinite queuing capacity, however, the calling population was infinite because we do not know the number of entities that will come, okay, at the end of the day. Now, we would also have the finite population queue model. An example is a textile factory with 15 sewing machines and a maintenance team. All right. When there's a breakdown on this machine and the maintenance team decide to work on the machine, we'll be sure that the machines do not exceed 50. They cannot exceed 50 because we already know the total number of machines in that factory. That is an example of finite population queuing model. Thank you for watching this video. In the next class, we'll continue from here. Do have a wonderful time.